Hello, my name is Kevin, and today I'm presenting to you my results from the lab I conducted about the motion of a falling object. And here is a brief overview of what we will be covering today, starting from introduction, the observed model, the computational models, comparing the models, as well as the conclusion. The question we should be asking ourselves for this lab is, how big of a part does drag force play in the motion of a falling object? First things first, let me go over the conditions of this experiment and the steps taken for this study. The experiment itself consists of dropping an object straight down from rest, which means with no initial velocity. I chose to use a catball that I dropped onto the ground, then I analyzed the motion of the object through tracker, and next I constructed two computational models using GlowStrip, describing the theoretical motion that object could have, which is largely based on a momentum principle. So we'll see in a bit what the difference is between these two computational models, and then finally I will also compare the results by plotting all three position versus time graphs on the same set of axes via Microsoft Excel. So in the next slide we will see a more in-depth overview of this lab experiment to answer this question. After filming the video, I imported a tracker and selected the frames I was interested in. These are the frames that show the object in free fall. This means that I skipped the first few frames as well as the last few frames when the cat ball was initially in contact with my hand as well as when the cat ball was in contact with the ground. So to specify the length scale of my video, I used my counter as the reference, and I chose this coordinate system which I arbitrarily oriented in a standard way and set the origin to be the center of the cat ball at the beginning of its motion. Next, I manually track the position of the object's center of mass for each of the frames I selected. This way, the tracker associated a certain position along the y-axis to each time and position plotted versus time graph. So one thing that I must note is that in tracker, I was unable to orient the axes, so the x-axis will technically be my y-axis, but the video it will be pretty apparent. So now we will discuss the GlowStrip computational models, which involves the code, the system properties and initial conditions, the calculation loop, as well as how the program is ran. So now this is the script I use my force computational model. For the system properties and initial conditions, I weigh the object and set its initial mass to 0.001 kilograms. Then I specify the initial position as well as the velocity vectors to be 0 because this is in accordance with the condition I experiment. You can also see that I set several variables that will also be useful later on. G as well as J hat and B. So B represents the proportionality constant used to define the drag force, which we'll see right after. So next in my while loop, I also set the time to be smaller than 0.35 seconds because that is how long the fall was according to tracker. Also set my net force to be sum of the gravitational force and the drag force. The drag force has a magnitude proportional to the square of the object's speed and a direction opposite to the motion, so upwards. Finally, update the position and the position formula and to update the velocity formula. As you can see here, when my code runs, it plots the position versus time as well as the velocity versus time graphs, as well as print the values of time and position, which you'll see in the following slides. So quickly to summarize, for my first model, I set B to 0, so net force will be equal to the gravitational force. And for my second model, I set a B to 0.001 so that the net force will also count the drag force. So before we go into more detail about the analysis, here are some of the results. As we can see on the left, when the net force involves only gravity, there is a shorter duration in terms of the time compared to the graph on the right, which involves the drag force as well, where the cat ball took slightly more time to reach the ground. Now that I have obtained three position versus time graphs, I plot them together thanks to Excel to compare them. First of all, we can see that all three graphs are a parabolic line of position versus time, and overall, the slope of the lines keep getting bigger. We can infer from this that during the fall, the cat ball was not going at constant speed, but rather accelerating due to gravity, and as well as the net force and gravity. So let's talk a little bit about differences between these models. While the second computer model here in gray has a slightly different trajectory than the track model here in blue, they still will have the same final y position, so we can consider this model as rather realistic. On the other hand, the first computation model here in orange predicts quite a different final y position from the other two models. Now let's talk about terminal velocity by having a look at our two computational models, velocity versus time graphs plotted on GlowStrip. In the model of just the weight, the drag force is 0, so we can easily say that it does not counterbalance the force of gravity and that the cat ball does not reach its terminal velocity. The same can be said for a second model, which we will find that it also does not reach terminal velocity. But what about if instead of dropping the object downwards from rest, I've thrown it downwards from initial velocity? We can have a look at this velocity versus time graph. First of all, the graph will result in the speed of the cat ball having been larger, where in other words, the duration of the fall would have been shorter, and it's possible that the cat ball would have reached a terminal velocity. And later on in the future in the class, we can all see that this relates to energy, versus like 1/2 mv squared. As you can see that the height leads to greater velocity in the end. So what can we conclude? In conclusion, I want to say that our computer model, which does not take into account the drag force, was pretty far off from the other two models which did. This means that taking account into area resistance while predicting the motion of the following object is quite important. In our specific case, it should not be considered negligible, or the final result will not be exact. So thank you for listening. Also wanted to add that the drag force is dependent on surface area, which we will need to consider. However, in this case, our object was a ball, which is rather small in terms of mass and also had a low surface area.